Here's a quick video to help you hopefully understand the lab quiz that we had about molar volume. Try to explain the why we have to do things. Maybe that'll help you understand better what you need to do when, rather than just trying to remember the order to do things. So, what do we got going on? We are reacting one kind of substance with extra oxygen to make two other kinds of substances. The only ones we're really concerned with are the lead sulfide, because that's how many grams we started with, and the only product they're going to talk about is sulfur dioxide gas, and that's what they're going to be asking us about. So I've got almost like a BCA table ready, but I really only need to understand lead sulfide versus sulfur dioxide. This is a gas. It will be collected over water. There's no way to bubble any gas up through water without getting some water molecules mixed in. The good news is scientists have figured out how many water molecules, or at least how much pressure caused by the water molecules, so that we can subtract that out. We'll come back to this table of temperatures versus pressure of millimeters of mercury in a little bit. So one of the things that we're going to need at some point is we need to figure out how much stuff are we starting with. This says there's 259.2 grams of PBS, or lead-2 sulfide, and everybody knows that 1 mole, no, everybody doesn't know this, but I added it up, it's 239.2 grams. We have 1.08 moles. One of the things we should do is calculate moles of reactant. The reason we need to know the moles of reactant is because that helps us predict. If I write 1.08 moles here, I've got to look at the mole ratio of this to this. That means that we should get 2 makes 2, so 1.08 will make 1.08 moles of SO2. That's one of the things that we have to do. This gas was collected over water, like was mentioned, and so in order to know how much gas we had, well, gases occupy different amounts of volume at different temperatures and also different pressures. So we kept track of what the barometer said that day. In this case, the barometer said that it was, can't find it, 767 millimeters of mercury. But since it was collected over water, not all of that pressure had to do with the product that we're after, sulfur dioxide. Some of it had to do with water. How much? Well, since it was 25 Celsius, at 25 Celsius, 23.8 millimeters of mercury are going to need to be subtracted. 23.8 millimeters of mercury. 767 minus 23.8, and that's 743.2 millimeters of mercury was due to that. Subtract pressure due to water vapor. Each temperature has a different amount. You either need a table like this, or it might say it inside of the problem. Okay, what's next? So here's what we know so far. We know that we are producing 1.08 moles of SO2. We also know that we're collecting it as a gas, and the gas was at 743.2 millimeters of mercury. It's time to figure out, since when we're looking at this, we're going to be looking up things about STP, standard temperature and pressure. It's time to figure out how much gas do we have, and what volume would it be if we made it standard temperature and made it standard pressure. Get rid of that. And so I'm going to make one of these boxes that keeps track of the pressure and temperature and volume. I don't even need the N, because we're not changing the number of moles in there. So this gas, which we collected, this 1.08 moles of sulfur dioxide, well, this gas was at this pressure, 743.2. I know it was really at 767, but part of that was water. What if we change it to standard pressure? Standard pressure, 760 millimeters of mercury. It's in our notes. It's not a secret, 760. This gas was at 25 degrees Celsius. When we're doing gas laws, we have to make sure we add 273 to turn it into Kelvin. So that's 298 degrees Kelvin. What if we made it standard temperature? That would be 273. So we're trying to take a volume of gas they collected. Let's find it. They collected 22.7 liters. We're trying to take 22.7 liters and figure out what volume would it be if we made it standard temperature and pressure. So I ask myself the question, well, if we change the pressure from 743 to 760, what is that? That's an increase. That's an increase in pressure. But pressure and volume are inversely proportional. That will cause a decrease in volume due to the pressure. So I'll just make a little note to myself. But if we change the temperature from 298 to 273, that's a decrease. Temperature and volume are directly proportional. A lowering of temperature would cause a lowering or a decrease in volume due to that temperature. I'm going to use these arrows to set up these next two fractions. It wouldn't be 22.7. It would be smaller due to the pressure. So I take the smaller number of pressure, 743.2, and put it on top of the bigger number, 760. It also is going to get smaller due to the temperature. How do I use the ratio of 273 to 298. How come I put the 273 on top? Because it's smaller, and that's going to make for a smaller number. When I calculate that all out, turns out that amount of gas, if we would have changed it to standard temperature and pressure, would be 20.33 liters. What's it supposed to be? Well, we don't know. What we do know, there's this information that we know that 1 mole of any gas at 1 mole of gas at STP is 22.4 liters. So if we had exactly 1 mole, we could compare 22.4 to this number. Did we have 1 mole? Nope. We have 1.08 moles, or at least that's what we should have. If we start with exactly 1.08 moles of lead sulfide, we should end up with exactly 1.08 moles of sulfur dioxide. So what we need to do is account for the fact that what if we didn't have 1.08? What if we only had 1? So the math looks like this. 20.33 liters resulted from 1.08 moles. I'm going to set that equal to another fraction. It's just a proportion. What if we would have had 1 mole? How many liters would we have? And I'm going to call that x. And it's kind of like a cross multiply. But technically, this is over 1. So x is simply equal to 20.33 divided by 1.08. And that's equals to 18.82 liters. So, had we had just 1 mole of the lead sulfide, we didn't, we had 1.08, but had we had 1 mole, it would have only occupied 18.82 liters. But scientists tell us it was supposed to occupy 22.4 liters. So what is my percent error? That's observed minus accepted divided by accepted, however much they differed, divided by what it was supposed to be, times 100 to equal a percent. So it looks like this. What did I observe? Well, I observed that it should have been 18.82 liters. What was it supposed to be? 22.4 liters. You're going to get a negative number here. Just use the absolute value. Don't really talk about that much, but that's what it should be. Divided by the 22.4 liters. Careful when you put this into the calculator. When I do this, I'm going to do 18.82 minus 22.4. Then I'm going to press equal. It's that number divided by 22.4. But I have to times it by 100. I could keep the negative. I'm not going to. I'm just going to simply round and get 16% error. It's off by 16%. If I kept the negative, maybe it would tell me that it was short by 16%. That is molar volume of a gas lab quiz.